All right. Yeah,
All
so
yours.
I have to first admit something. I have written down that we're in beautiful Warsaw. I so far have seen the airport and the hotel. So my assumption is that it's true, and I hope to see that this week. But I'm a PhD student from Radboud University. And I'd like to tell you a little bit about ultracold molecules and specifically the application to molecular quantum computers. So let's, if this works. Ah, yes. So let's jump back in time a little bit. We have this handsome fellow called Richard Feynman, and he said, well, nature isn't classical, beep, and if you want to make a simulation of nature, you better make it quantum mechanical. And this kind of sparked the idea of quantum simulation and quantum computing. One flavor of this will look something like this. This is an array of particles, where every particle, like atoms for example, represent qubits, so basically the information that is stored into a system. Now, to actually make a computer out of this, we need communication at large distances, gates, or logical operations, essentially. And for this, we need long-range interactions, which atoms generally don't really have. A lot of physicists like to go to Rydberg atoms, highly excited states, that actually show some dipole-dipole-like interactions. As a chemist, I also see an alternative. Why not use molecules? And molecules also have this dipole moment, even a permanent one, that is present basically in the ground state of molecules. For example, for a Rydberg atom, it's in an excited state, so you might have spontaneous emission, which is not prevalent in molecules. So for these systems, we need ultimate control, and for that control, we need to go to ultra-cold temperatures, where we use molecules that are slightly more exotic to the average chemist, but we've seen a couple so far already today. For example, the bialkalis, but also laser-coolable molecules like calcium fluoride, and even polyatomic ones like calcium hydroxide. These might all be interesting candidates for these quantum computers. All right, so what is the platform that we're actually working with? Well, the platform is the one of optical tweezers. So this is a grid of lasers, and in the end, we want every laser to have a single molecule. So we basically chuck in our favorite ultra-cold gas, and we let them cool down using laser cooling, for example. And we can then load in these, or I should say, some of these molecules will be loaded into these tweezers. Now, to actually build a working quantum computer, we need a defect-free array. So what needs to be done is a lot of rearrangement. This can be done. This is fine. And we then kind of end up with some kind of grid of particles. Now, for atoms, this has already been established. So we can see, for example, people have been able to load in hundreds of atoms in a defect-free array, and recently even 6,000 atoms have been loaded into such an array. Now, for molecules, how far are we? Well, not as far. So some people have been loading in, so especially in the US, in Princeton and in Harvard, they've loaded in calcium fluoride, but then very recently also calcium hydroxide, but we're reaching maybe a couple dozen. But the field is going very fast, so let's see whether we can improve on all of this. And one of the main questions here is really the efficiency of this loading before rearrangement. Because what is this efficiency really? Well, it's 50%. And this 50% is something that we really need to improve on. Before I kind of tell you how we're going to improve on this, let's show a little bit why this is the case. For the experts that might already do atomic loading, this is something you might encounter in light-assisted collisions. But for molecules, actually, it comes from a slightly more fundamental viewpoint. So this is something that we call collisional blockade. Collisional blockade, here the idea is we have some kind of trap. This is one of these tweezers. And during cooling, a molecule might fly in. This is great, let's stop here. But oh god, another molecule might come in. And if molecules like each other very much, they start colliding. And especially for the kind of reactive molecules that we're using, this generates a lot of heat. They fly out of the trap because we're working in ultra-cold temperatures. This just flies out. And basically we lose every collision that happens. So the reason we then reach 50% is during loading we might load an even or an odd number of molecules, and that basically then gives 0 or 1 molecule in the end in our grid. Now, why is this an issue? This is a very stochastic process. 50% is loaded, and as I said, we need to do a lot of rearrangement. Now, that rearrangement takes a lot of time. If that rearrangement takes longer than the lifetime of the molecules, we're in kind of trouble, because at some point we can't scale our array to bigger arrays. And if we're aiming to build large quantum computers, we need a more deterministic approach, where kind of this loading efficiency will get to 100%. So we have to do zero or little rearrangement as possible. And so how should we aim to improve this? Well, the one thing that we might be able to manipulate are these collisions. And at this point, I should say I am a theorist, so I can calculate things about collisions and kind of propose a scheme that might work very well for these applications. So in very, very brief slide, let's show a little bit of the theory and of what I can actually calculate. So what I'm working on is the Schrödinger equation. So I have a collision, so we have some kinetic energy, otherwise there's no collision, and we have some interaction between the two molecules. I throw that into a black box that I call quantum scattering, bunch of angular momentum theory and whatever, but what basically is happening is we have some interaction where these molecules, they collide as matter waves at low temperatures and they go out as matter waves again. The nice thing of these ultracold collisions is that I can say, well, at short range, whenever they get too close to each other, we lose them. So this we kind of impose as a boundary condition, and then we say, okay, well, I only really need the long-range interactions, so I don't need accurate ab initio potentials here, and I can actually calculate a rate of losing these molecules. Now, unfortunately, we don't have one potential. We're working with molecules. They have very rich internal structure, so that means a bunch of coupled potentials, and these calculations will become quite hefty, but we can manage these within the span of hours of calculation time. All right, so what is some of the results that we found that might be very interesting for this application? We've been looking at molecules in different rotational states. So let's look at how molecules collide in different rotational states. Let's put them both in the first excited rotational state, for example. Main thing is they're both in the same state. This kind of leads to these fast losses that I've spoken about before. To put this into perspective, for calcium fluoride, kind of the quintessential laser coolable molecule, we would lose about 3,000 molecules a second, and that actually won't cut it for our applications. Okay, so what we can do, we can manipulate these molecules. So let's shine microwaves, for example, on these molecules, and we can excite one of them to a higher rotational state. Okay, so let's see what these losses will be. Let's see whether they're favorable. Well, these are very fast losses by another order of magnitude. Okay, I don't like where this is going, but for the sake of science, let's just take it one step further and kind of collide molecules that are 2 or more quanta apart. And interestingly enough, these suddenly are very stable by a couple orders of magnitude for calcium fluoride. Now, the first 2 options have been studied in great detail. Molecules in the same state and molecules that are 1 quantum apart in rotation show very strong dipole-dipole interactions. So for dipolar physics, this has been of incredible interest. But the one here, we've not seen anywhere in literature at all, and that's kind of why we've studied it. Now, the real question is, why is this the case? We can understand it completely, so let's look at some interaction potentials. Let's look at it step by step. So if we have 2 molecules in the same rotational state, we basically have, what I show here is the interaction energy between the 2 molecules, so the potentials as a function of the distance. And as they collide, they come from the right, they go to the left, and it's an attractive potential because you have some attractive van der Waals interactions that are generally well known. So they go so as 1 over r to the 6th, and that leads to these fast losses. Now, if you put the 1 quantum apart, I now have a y-axis that is times 100, because these interactions are very strongly dipolar, because the energy level of 1 plus 2 is the same as the energy level as 2 plus 1. And that kind of in a first order gives a 1 over r cubed interaction that is that leads to very fast losses. Now, the cool thing is, once you put them 2 or more quanta apart, we suddenly see a barrier appear. That is not something that usually you see, because this actually is a repulsive van der Waals interaction that purely stems from the rotational structure of these, rotational kind of quantum structures of the levels. I won't get into detail of that. You can ask me later if you'd want to. We understand all of this very, very accurately. So in the long range, when something that becomes repulsive, at some point they start to polarize each other again, and it becomes very attractive. But this peak is about, for the molecule I made it here, was about 300 microkelvin, which is cold, but we can get colder in collisions. So actually, if we actually collide molecules at these very low temperatures, we can make use of this barrier to prevent getting into the short range and kind of shield the collision and completely, or not completely, but kind of eliminate the losses that would be present during collisions. So let's use this fact. Let's use this fact to actually create a more deterministic approach to loading a tweezer array. What we propose as a scheme is the following. If you take regular loading as normal, so this 50% that I kind of showed before, we then say, well, why not pump them up to a higher rotational state? Then it looks something like this. So this is kind of a grid now, 50% filled with molecules in J equals 3. These we will call storage states, because what we're going to do now is to say, well, we can repeat the procedure. We can do it again and reach higher and higher loading percentages. So why is that the case? Well, the cool thing is, if these J equals 1 molecules are loaded in an empty tweezer in a later cycle, completely fine, they'll get pumped to J equals 3, all good. It can happen that they're loaded, so new molecules are loaded into a kind of a storage tweezer, then the interaction, as I said just now, is incredibly repulsive, so this is a very stable interaction, and these new molecules will not destroy the already present molecule. Now these will do their regular collisional blockade, so if there's an even amount, these get cancelled, and then this one actually remains stable during the entire procedure. You can have that one molecule is left, but the nice thing is, because this molecule here is present, and due to some interactions between these energy levels, this J equals 1 molecule will not be excited, so you don't end up with multiple molecules in a single tweezer. At the very end, we can kick those J equals 1 molecules out again by using lasers, and what we're ending up with is a grid filled with single molecules. So I've basically run calculations for calcium fluoride, and I can show that within only 3 of such cycles, you could bump up this 50% to a more staggering 80% efficiency. And since this rearrangement really scales quite badly with the loading percentage, this is a major improvement and is getting close to what they can now do with atoms. So with that being said, let's jump to the conclusion. We kind of aim to improve the scalability of quantum computers made of molecules. And we propose a scheme to deterministically load them into these optical tweezers. And for that, we specifically use the rotational structure of the molecules that allow for very low collisional losses. With that, I'd like to thank my supervisor Thijs, our collaborator Mike, basically my institute, my group, and everyone else. And with that being said, let's aim for maybe the Guinness World Record of largest molecular quantum computer. Thank you very much.
Thanks. Okay, so I'm not sharing microphone. No, it's just there is another one. That's why.
Okay, thank you very much for your nice presentation. I have 2 questions. When you mentioned the possibility of having your molecules trapped by this activation barrier, and you mentioned that that could be possible at low temperatures, my question is how low? Because it's not clear from that which temperatures you have to reach.
Yeah. Let me go back. This is a little bit delay on the... Oh, there we go. So this barrier height, so actually these potentials I've calculated for the molecule sodium potassium. So the barrier height depends a lot on the specific molecule you're studying. I noticed that sodium potassium especially works very well for this interaction at least. So this barrier here is about 300 microkelvin high. So if you want to make use of this barrier in a way, you need to go to collision energies that are lower than that. So most of the calculations I've run are done at 1 microkelvin, because these are usually also kind of the experimental temperatures that they can reach for these molecules. For calcium fluoride, the barrier is a little lower, but still, if you're working in 1 or 10 microkelvin temperatures, which is really low but manageable, then you can actually make use of this interaction. No, thanks.
Thanks.
Great talk. So I wonder if you mentioned that you could get a little bit more into the details of why J1 plus J3 gives you this barrier, where this barrier comes from.
Yeah.
For example, would it say, how would J equals 2 plus 4 look?
Similar.
Or similar.
Yeah.
So
No, let me jump to a bonus slide, because there are always too many bonus slides. But I have, where was it? Here. The idea for these kind of long range interactions is that you can do some perturbation theory on the dipole-dipole interaction. So usually what we're interested in is the second order dipole-dipole effect. Usually that stems from some transition dipole moment to a higher electronically excited state. But we're now actually working with molecules that have such a strong dipole that actually we're looking at second order effects with other rotational states. Does not mean quantitatively you cannot neglect higher electronically excited states, but qualitatively everything can be explained using purely rotational energy levels. So for example, if you put both molecules in the same rotational state, you can couple to a state in dipole-dipole where you have to change every quantum by 1 to a 1 plus 1 state. That's the state you can couple to, and in second order it gives a kind of splitting between these two. That means that this lower state goes down by 1 over r to the 6th. So that's kind of the usual attractive van der Waals interaction. If I now jump to the other thing here, is where you have them 2 or more quanta apart. You can couple to kind of all these different other states, but specifically, if this one is high up on the rotational ladder, kind of virtual de-excitation of this and virtual excitation of this one yields a total energy that is slightly lower than the original state. So there's always going to be, and this holds for any time you have 2 or more quanta apart actually. And then you couple to a state slightly below in energy, and that always pushes up basically whatever this is by 1 over r to the 6th. And that gives this long range repulsive interaction that you see.
I see, thanks. So
That
it's a
answered it?
mixing of states that causes this effect?
Yes, yeah, it's a second order effect purely from the rotational states of